Okay.
It's a slideshow. All right, here's the slideshow. Excellent. Okay, this is me. uh, the Heliophysics Big Year is an interesting celebration of 14 months worth of interesting themes having to do with the sun and related subjects. As a new word, which you won't find in the dictionary, heliophysics is the study of the sun, solar interaction with the planets, and the physics behind those interactions. Hence, helio and physics live together in the same word, and all of that. So, what we did with the heliophysics big year idea is we started it in October 2023 with the annular eclipse. Midpoint was the total solar eclipse last April, and then we have the Parker Solar Probe encounter with the sun this coming December. So that gives us 14 months of interesting themes. The themes were designed by Nikki Fox at NASA, and there's a nice YouTube video you can look at that describes the individual themes. But, kind of the idea that the sun impacts us in a whole lot of different ways. And so this was sort of a celebration of all those different ways that the sun interacts with us and with other things in the solar system. So this theme is basically October. It's solar cycles, which I very loosely define as sunspot cycles and related things. Not a very imaginative interpretation of that theme. But when you look at some of these other themes, like in February we had fashion. That one took me a lot of head scratching to find something in heliophysics that had to do with fashion. But it turned out that fashion is often all about color. Color is a feature of light, and light is something that we study when we investigate the sun. So, it wasn't too hard to come up with something that went along with that theme. Anyway, solar cycles. NASA's heliophysics division, or its approach to science, can sort of be summarized in three major big questions. What causes the sun to vary? How do the Earth and the heliosphere respond to that? And what are the impacts on humanity? It's always the bottom line. What are the impacts to humanity? Why should I care? Why should I invest in this research? What's it going to do for me, at my kitchen table and things like that. So we cover just about everything. What we have also done, NASA HEAT, is to create a framework for how to cover these topics within the National Education Standards in Science. And so for that, you can go and look at our website and see how that all plays out, how the different questions map into the particular standards that teachers have to teach by and target. These standards come, again, there are three major questions. We've created three subsidiary questions under each one of those, and those subsidiary questions are more directly related to the education standards that are at play in K-12 education. The thing is that these questions are also of interest to non-educators. It's a way of, focusing even more narrowly on specific things that go on with the sun. So this framework actually provides you with a kind of a map, an idea map, for how to ask questions about the sun, starting from the big ones and going all the way down the tree to, some fairly refined questions that you might want to think about or get information about. Well, okay, I'm sorry. This talk this evening, we're going to connect up with the sun defines the space around it, which is different from interstellar space, and standard, 3.1 subsidiary question. The sun is made of churning plasma, causing the surface to be made of whatever magnetic fields and such. And so basically, this all wraps together into aspects that have to do with solar activity, sunspots, and sunspot cycles. It sort of forms that basis. Now, a real practical demonstration of the sunspot cycle. Well, we got a real eyeful last weekend, depending on where you were. What we got down here in the lower 48 were chromatic aurora. They are produced by some of the more violent solar storms on the sun. And we know that storms on the sun that produce aurora are pretty well tied to the ebb and flow of sunspots on the surface of the sun. We are at what is called sunspot maximum right now, or close to it, where we have sort of the largest number of countable sunspots on the surface. If you get a telescope with the right filter, you can count these things down to the resolution limit of the telescope, and that gives you a gauge for how active the sun is. Clearly, you don't expect to have a lot of storms if you don't see any sunspots, because that means that the sun is not especially active or doing anything particularly violent. It turns out that this ebb and flow of sunspots is not random. It's been known since the 1840s that it comes in a roughly 11-year cycle, going from minimum, when there are essentially no sunspots to be found on the surface with the telescope, to a maximum and then back down to a minimum again, taking anywhere between about 9 years and up to as much as 12 years. But the average is about 11 years. Sunspots are really wicked complicated. They're produced by magnetic fields that pop up from the inner layers of the sun. They punch through the photosphere because they become very buoyant, kind of like balloons that you release with helium in them. And when they breach the surface of the sun at the photosphere, they produce magnetic fields that then expand out into space, and you get these wonderful arcades and prominences and things of that nature. It turns out that because a lot of the surface activity is controlled by magnetism, at least the detailed activity, magnetism, of course, has a polarity. It's north and south. And it turns out that when sunspots are born, they tend to be born at the higher latitudes of the sun during the early part of the 11-year cycle. And then as the cycle winds down and gets more progressive, the sunspots tend to be formed more frequently at the lower latitudes. So you wind up with the figure that you see on the right, which is coded by north-type magnetic polarity as red and south-type polarity as blue. And you can sort of get the gist that that these spots are formed with different polarities. As the cycle progresses, the sunspots are formed in the lower latitudes, as I said. So you get this very characteristic, what's called a butterfly diagram. Each one of these cycles has its own butterfly shape. And the details are kind of interesting because you'll notice that the overall magnetic field of the sun is sort of that background color. And in cycle 21, if you look at the top, which is the north pole of the sun, the blue coloration means that it was a south-type polarity, magnetic polarity, at the north geographic pole of the sun. 11 years later, cycle 22, it became south-type. And then finally, 11 years after that, in cycle 23, it became north-type again. So it turns out that the sunspot cycle determines the individual ebb and flow of sunspots, but there's also a 22-year cycle that determines how the sun returns to its original magnetic polarity after 2 of these cycles has transpired. This is called the Hale magnetic cycle, and you might hear reference to that on occasion. There's a lot of detail in this figure, and I'm sorry I can't spend a whole lot of time with it, but this forms the basis for some of the models that we now have of the lower surface layers of the sun and learning about why the sun has a surface magnetic field in the first place. The overall goal by solar physicists is they would eventually like to be able to predict how many years a sunspot cycle has for a particular cycle, all right? Some will be 11 years, others might be 9, others might be 12, and also the strength of each of these sunspot cycles. Some are going to be very weak, like the current cycle is destined to be a fairly weak cycle. Others are extremely strong, like the ones that we had in the 1970s and 1980s. We still don't have a rigorous way of predicting from observations that we can make exactly how a particular sunspot cycle is going to progress. So that's really a real challenge today that people are working on. So here is 400 years of sunspot observations, and you can see there's a definite heartbeat to the sun since about 1750. As I said, the peak, how strong these cycles are, seems to be kind of unpredictable. Some claim that there's a 90-year or so period in terms of the maximum peaks of these cycles. But in general, they really don't seem to have any relationship between one and the other. And this is ultimately what physicists want to be able to predict. They want to be able to make a detailed model that actually gives back exactly that kind of a plot so that we can predict how strong the sunspot cycle is going to be in the next 11 years. Because it turns out, NASA is planning on doing things in the future and would like to know under what conditions the astronauts are going to be operating and how severe the sunspot cycle is going to be, which is an indicator of the types of solar storms we're likely to encounter during that period. So that's one of the real goals here. The last few light cycles are likely the ones that you've probably heard of since 1975. Let's see, 1975 to 1985, I was in graduate school and getting my first job. 1990 to 1995, I was working with Kobe. You can sort of plot your entire life and events in your life on top of the sunspot cycle. And so here we are in the period between 2020 and getting up towards 2025 sunspot maximum. And likely there are going to be plenty more of these cycles to come. And so it's interesting to try to predict when they're going to happen. The current cycle looks kind of like this, which is why solar physicists are saying that the current cycle is probably not going to be really any more severe than the previous one was. Of course, I mean, you might experientially wonder, well, when was the last time that I saw an aurora in my backyard from, someplace in the lower 48? Well, during the last sunspot cycle, you were also able to see these things, not as dramatically. These things don't come with any regular period or regular intensity. But, if you lived up in Canada, you would certainly see the ebb and flow of aurora in your skies that sort of very accurately matches this kind of a sunspot cycle change from more aurora to fewer aurora. For instance, 2020 was a very bad year for seeing aurora, and that's likely to be repeated in the year 2031 when the current sunspot cycle is over. So don't plan any cruises or journeys to Alaska in the early 2030s to see aurora. There probably aren't going to be any during the time that you'll be traveling. Keeping track of the sunspot cycle is a way of anticipating when we're going to have severe solar storms. Some of these solar storms produce intense bursts of radiation and X-rays. The X-rays aren't especially harmful to humans operating in space, but the energetic particles that come from other types of storms, like coronal mass ejections, are really hazardous to humans. And so you want to have a way that predicts when the next one of these things is going to happen. So there's a huge amount of effort theoretically and computationally being expended to making better and better predictions of when these radiation storms are going to happen. Okay, let's have our first encounter with some interesting math. As a beginning introduction to sunspot cycles, let's do the following experiment. Assume that the cycles obey the following rules. The period is 11 years. The maximum is July 2024. That's close to when the current maximum is occurring. The minimum, well, we just experienced that. That was in January 2020. And the height, well, let's not worry about the height too much because that's not something that we can model as reliably as the period. So the question is, when are the next 3 sunspot cycles going to occur? We want to tabulate and plot the years of those cycles, the minima and maxima. And we're going to assume that all the peaks have an equal height to the cycle 25 sunspot maximum. Again, we're not really worried about the height, but we would like to get the times, the calendar times, at least reasonably correct to within, a half a year's accuracy would be a good target goal. So the way that we set up that problem is sort of as follows. We're going to start with cycle 25, which is the current cycle. And you'll see that July 2024 was the maximum and the minimum was January 2020. So we're going to convert that into decimal years. Then to get to cycle 26, we just simply add 11 years to those decimal values. And we get the maximum for cycle 26 as the year 2035.6. So it's sometime July-ish of the year 2035. And the minimum is going to be somewhere around the year 2031, January-ish. That's just simply by adding 11 years. We can then do the next 2 cycles, 27 and 28, get our complete 3. Again, just adding 11 years to the maxima and minima, we get the things that you see for cycle 27 and 28. Unfortunately, I can't see what the years were for the minimum because it's covered by this lovely gallery of images from our talk, and I don't have any way of moving that off to unblock. But the minima are going to be in 11-year intervals. So 2031 for 26, for 27, it's going to be 2042. For 2028 is going to be 2053. I believe that's what is shown here. But anyway, we get an idea for the next 3 cycles when we should expect sunspot maximum and sunspot minimum. And if we plot it, instead of tabulating it, we could get something like this as a plot. Here, I've just used a sinusoidal period, and I folded it so it looks like this. If you're in electronics, basically, I've DC rectified an AC signal. I don't know if that helps you understand what's going on here, but basically, this is what you get when you put an AC signal through a diode bridge. You get basically just a DC thing that looks like this as an output. In this case, it's the minimum for sunspot numbers is always 0, and the maximum is always going to be at the maximum. And as I said, we're not going to worry too much about the peak. What we are interested in is when the zeros occur and when the sunspot maxima years occur. So this is what you get. And to first order as an approximation, this is not a bad representation. If you went backwards in time and predicted what the previous sunspot cycles looked like, you'd get a fair match to what was actually observed. I mean, the amplitudes would be different. They'd look a lot rattier because you're using real sunspot number data. But in general, the trends would be about the same because for the last 100 years, the average period, the average time between sunspot minima has been about 11 years. So we're always going to get that roughly correct to within a year or 2. Intermediate, here's a challenge. It turns out that cosmic rays, I mean, sunspot cycle is one thing because you're counting essentially how many sunspots, how active the solar surface is. And that correlates pretty well with how often you should expect to see brilliant aurora or radiation storms or coronal mass ejections or any number of other active phenomena. But it turns out there's a second component of hazardous things that goes on in interplanetary space, and that's cosmic rays. Cosmic rays come from outside the solar system. They often come from nearby supernova remnants. They can also come from supermassive black holes in distant galaxies, and even from the galactic center. Black holes are an especially good powerhouse of producing cosmic rays, and I don't want to get into that in too much detail, but cosmic rays are something that you got to worry about in the solar system because they are much higher energy than the solar radiation particles, which are mostly protons. So if you're traveling through interplanetary space, if you try to make the journey during sunspot minimum, you actually run into a problem. It turns out that when the sun's magnetic field is the most extended in the solar system, that's at sunspot maximum because the solar surface is very rich in magnetic fields, and many of them open out into interplanetary space. It turns out that that extended magnetic field of the sun is a good umbrella against many types of cosmic ray particles. They have a harder time getting into the inner solar system during sunspot maximum. Conversely, when there isn't much activity going on the surface of the sun during sunspot minimum, cosmic rays have more or less free access to the inner solar system. So the net result is when you measure cosmic rays and how they change in time, they are almost exactly anti-correlated with the sunspot cycle. When the sunspot cycle is high, you get the lowest number of cosmic rays. When the sunspot cycle is at minimum, you get the largest number of cosmic rays. So now here's the dilemma. You want to track both of these cycles because both of them imply hazards to astronauts. Certainly the cosmic rays, you don't want to be irradiated by cosmic rays as you travel to Mars. And they're a constant background. They're always present, all right? They don't have any intrinsic variability. The sunspot cycle and those active regions, however, they change with the solar cycle. And so you want to also pay attention to when you have a lot of possibilities for active regions on the sun to produce energetic particles. So if you're an interplanetary traveler trying to minimize your radiation exposure, you literally are caught between a rock and a hard place. And it's a very narrow razor's edge that you have to travel in order to make sure you get the minimum radiation exposure during your journey. So in this particular activity, which is sort of intermediate level math, you have to create a model of both the sunspot cycle and its 11-year change, and also a model for the cosmic ray cycle with its roughly 11-year change, but anti-correlated with the sunspot cycle. And here's how we can do that.
Here, I don't want your pictures.
I'm sorry?
I do.
Okay. What we want to do is draw a second curve on top of the sunspot cycle curve.
Mike?
I'm sorry?
Echo. It's not a problem.
Okay, I'm hearing somebody's voice. That's
Somebody has an open mic.
Somebody has an open mic.
Yeah.
Okay.
Could you guys just check?
All right. So anyway, what we're going to do in this particular case is essentially the same thing that we did for the sunspot cycle. We take advantage of the 11-year period. Now we have cosmic rays at a minimum at certain times and cosmic rays at a maximum at certain times. And so we just basically do the same thing. We predict the next 3 cosmic ray cycles the way we did the next 3 sunspot cycles. And we can plot those on the same plot, and we get something that looks like this. The black curve is the sunspot cycle, and the red curve is the cosmic ray cycle. Again, I haven't bothered with the amplitude or the intensity of either of these cycles because, again, I'm more interested in the times when they occur at maximum and minima than I am in the actual intensity of these curves. All right, for purposes that I'll show later. Anyway, this is what it looks like. It's a sunspot cycle is one of these, and the anti-correlated cosmic ray cycle is the second curve. It kind of looks complicated, but very often this is what happens in science. You have a couple of models and you plot the models, and then you have to interpret the curves and not be too confounded by what things look like. You see that the whole strategy in mathematical modeling it requires a certain amount of courage. You can't let the data push you around. All right, it takes a real attitude on the part of the mathematician to create models and have some kind of confidence that the models speak to something real in the world. And just the very idea that you can model something that's going on in the universe, is a kind of measure of arrogance. And you have to be willing to be that arrogant as a scientist, as a modeler. And you get to be that arrogant, not without reinforcement from the world at large. Because it turns out the world at large and its data has all kinds of interesting patterns in it that can be very easily elucidated by using some basic mathematical principles. And when you apply those principles and make predictions, well, then you are doing a mathematical model. So you're not doing something that's just completely ridiculous. You're actually letting nature be your guide, using the data that it provides, and then making some reasonable extrapolations from that data to predict interesting things. And ultimately, we talk a lot about the pursuit of knowledge as this kind of pure and, sort of intellectually pure pursuit. But ultimately, it's tied to a very primal thing that humans have been doing for millennia, and that's trying to predict what's going on in the world around you so that you don't get killed or that something doesn't eat you. And so humans have learned mathematical modeling implicitly by, for instance, following the seasons and then estimating when is the best time to plant. We even build monuments as calculators for doing that calculation. Well, here we can use our hand calculators, to make this kind of a model and launch predictions from that. Well, what kind of a prediction are we going to try to launch? Well, we're talking with sunspot and cosmic ray cycles, things that happen over time scales of decades and even millennia. The kinds of things that we have in mind, at least in the near term, is that we see ourselves as wanting to be a spacefaring civilization. We're going to go back to the moon and set up a real bona fide colony there 50 years after the last time we visited. But beyond that, we like to be able to go to Mars. That's going to be a somewhat more daunting challenge because it's much farther away. And we're going to have to spend a lot more time in interplanetary space, reading our books, watching TV, and getting irradiated by cosmic rays and any gosh darn solar storm that's going on. So the question is, to make that journey short, we want to take that journey when Mars is closest to the Earth. That's called opposition. Okay. So we know when those opposition years are going to be. I mean, we can forecast those out to, 500 years in the future if we want. They happen roughly about every 18 months or so, give or take. And so this table shows the opposition dates when Mars is closest to the Earth. So these are really stellar times when we could send a spacecraft, a manned spacecraft to Mars with the shortest journey time. For current propulsion systems, that's about 200 to 250 days. Without taking advantage of this opposition effect, that number will be more like 300 to 350 days, depending on the random time that you decide to go. So clearly we want to wait for oppositions. But in order to minimize our radiation exposure, we also want to only travel when the cosmic ray cycle is at its lowest, and consequently the sunspot cycle is at its highest. Well, we already have a model that we think predicts when those times are going to be. So now what we want to do is combine the two and find some optimal years when we could choose to send somebody to Mars, humans to Mars, and at least get some kind of a guarantee that they're not going to glow in the dark when they get there. I'm sorry, that's a kind of a misconception. Just because you get irradiated doesn't mean you're going to glow in the dark. But I like to use it because it's good comic relief. So anyway, here's what we do. The opposition times in the previous table are indicated by those little red triangles. Red because Mars is red, triangles because triangles have three sides. You know, no deep meaning there. And then we have our sunspot cycle in black, and we have the cosmic ray cycle in red. And so now the question is, you know, based on the timing here, when might be the best times to take one of these trips to Mars? And that is going to be a date that NASA will look at very carefully with even more powerful predictive models. Hopefully by the time we get to that point, we will have solved a lot of theoretical models about predicting when sunspots will happen and when flares will happen on the sun. The progress of knowledge and modeling is going at breakneck speed right now. So probably by the time we get to one of these markers, we will have, you know, pretty good predictive models for when actual storms are going to happen. So anyway, here is one set of possible answers. There might not be any right answer, but each opposition has its advantages and disadvantages. I'm showing one set. Your students might want to argue in favor of others. Take a look at the first big blue arrow that happens at 2035. Here we have the sunspot cycle nearing its maximum, but you know, not quite there yet. And we have cosmic rays at way down. They're not at minimum, but they're pretty far down. And actually, in the way that the cycle works, they're on a decline. So the longer you wait after 2035, the fewer cosmic rays you might expect to encounter. However, if you delay to the next triangle to the right, you're at cosmic ray minimum, but you're at sunspot maximum. That means that you might not have to worry about cosmic rays contributing to your radiation damage, your biological radiation damage, but you will have to worry about, you know, how many of these severe radiation storms you have during those years. Interesting, radiation storms that are really severe can happen just about any time during the cycle. But the average ones tend to happen after sunspot maximum and persist up to a year or two. The sunspot cycle maximum through about a year or so after maximum is the time for the best viewing of really big aurora events. So anyway, if we look at the next large arrow, 2050, we are farther down on the sunspot cycle. In fact, we are starting to get towards the end of that period post sunspot maximum, when you can expect to see really big storms. But of course, we have the cosmic ray intensity starting to increase. So we're now being more bothered by the high energy particles that are entering our spacecraft through whatever shielding we decide to have. So anyway, and there are some minor arrows that I've drawn in here too. That first minor arrow at 2040 actually looks pretty good. Lower solar radiation storms, but again, we're starting to get much more of the cosmic rays, and ultimately the cosmic rays are the hardest ones to shield against. So this puts even more stress on our design of radiation shielding for spacecraft. The really bad thing is that the more energetic a particle is, when it enters shielding, the energetic particle slams up against the nuclei of the shielding material, and that spawns secondary high energy particles. So it's not like you can just simply increase the thickness of your shielding to protect you against the high energy particles, because the thicker the shielding, the more secondary particles you get. And so your ultimate radiation damage is even higher with the thicker shielding for these high energy particles. It's completely counterintuitive, but that's sort of the way the interaction between energetic particles and shielding tends to work. That's why it tends to be easier to shield against the solar particles because they are lower energy, and for a given amount of shielding, they will produce far less secondary the particles, energetic particles, than the cosmic rays will. So that's why we tend to bias looking at a good date to go to Mars more in favor of where the sunspot cycle is and times when the cosmic ray cycle is at the minimum, so that the amount of shielding that we need is really determined mostly by the energetics of the solar particles and not by the really hard to shield cosmic ray particles. So anyway, this is part of the kind of dialogue that a student or a lifelong learner can get into when they think about the sunspot cycle, the cosmic ray cycle, and taking a journey to Mars. There are a lot of really good discussions at many different levels of radiation, shielding, and exposure, traveling to Mars and the hazards of radiation effects. And this example here sort of plays into that by sort of showing you the behind the scenes math in a very, very simple model for how these things play against each other. Now, I'm fascinated by ChatGPT, and so I'm going to ask ChatGPT a very well-posed problem. Between now and the year 2065, given the sunspot cycles, the cosmic ray cycles, and Mars opposition distances, when would be the best years for astronauts to travel to Mars? That's the query that I put into the ChatGPT, query bar. And I assumed that it could figure out all the details itself about what I was asking it to do. And it didn't do such a bad job. First of all, it calculated all the opposition times, Mars oppositions. Then it calculated the sunspot cycles, and it did that essentially the same way that we did. And then it said, based on these factors, it came up with a couple of dates, 3 dates. It would be the best years to send missions to Mars. Well, the problem is that ChatGPT neglected to factor in the cosmic ray cycle, but it didn't tell you that. So these years are basically based solely on the sunspot cycle minimum, which is not the answer to the question. So this, once again, if you've been following my webinars for the last, 12, 13 times, I often put in a ChatGPT query just as a demonstration of how ChatGPT would handle the same advanced question. And a lot of the times it does a very good job, but sometimes it fails miserably. And the question is a very well-posed question, but yet it gives kind of a meaningless answer or an incomplete answer, and it doesn't tell you that it gave an incomplete answer. So, let the buyer beware. When you use ChatGPT, it works really well as an intelligent calculator, but you still have to check your answers. And in this case, you'll discover that it didn't give you really the full quart of milk. Not quite sure what the correct expression should be. Maybe we can invent one just for ChatGPT. They say sometimes ChatGPT hallucinates. Well, this might be a case of hallucination or just whatever. Anyway, okay, so that takes care of that. Next time, I'm going to talk about unexpected discoveries. And this happens in the middle of November. I will say no more about what the middle of November is likely to look like in this country, but in terms of heliophysics and the sun, I can guarantee you there are some interesting things that we're going to cover next time. in bonus science. So, okay, let me stop the share and I'll revert to the screen. And now you can send me your best questions.
We have a couple in the chat. One is that Adrian asked, are there these considerations about sunspots and cosmic rays also part of scheduling robotic missions such as Perseverance rover and Ingenuity flights?
That's an excellent question. Normally, energetic particles, these are typically protons with energies of over 10 million electron volts. Normally, they're a problem for satellites and satellite electronics. For instance, the communication satellites, they are not really heavily radiation shielded. So when cosmic ray particles interact with those systems, they can cause glitches, and various satellite outages. But for scientific experiments like the rovers on Mars or interplanetary space probes, we've been doing this a long time. We've kind of figured out how to properly shield things within a spacecraft so that it doesn't completely scramble the data. We have systems that basically are able to expunge glitches in the data caused by cosmic rays. We have backup command coders and a variety of other systems that are redundant that really protect us from these kinds of malfunctions. So yeah, I mean, we'll use the same radiation hardened technology for our probes on the moon. It's always the astronaut, however, that we have to worry about because all they have is a very thin spacesuit, which is almost transparent to cosmic rays. And so if you're out there during one of these if you're out there, you're always being hit by cosmic rays, and that increases your radiation dosage, hour by hour. And so we have to figure out, even for people working on the moon, we have to figure out a way of more robustly providing radiation shielding for them. And there are a number of interesting designs on the books for that.
Okay, and we have another question about the Hoffman transfer.
The Hohmann transfer?
And if you're assuming the minimum energy Hoffman transfers?
Yes. The Hohmann transfer orbit is really very clever because basically it uses the minimum amount of energy and it basically says we'll get there when we get there, but we have a minimum amount of energy that is fuel. So we're basically going to take an elliptical path that is tangent at the location of Mars at the time we want Mars to be there. And that really is the state of the art for getting anywhere in the solar system because essentially all of our rocketry relies on the huge boost that we get at launch, and then we basically coast the rest of the way. The only exception are the ion propulsion systems used on some spacecraft. They are constant thrust, and if you souped them up to the megawatt scale, you could get some very, very high thrusts that would let you continuously operate these spacecraft and take trajectories that are faster than the 240-day Hohmann transfer orbit to Mars. In fact, some of the designs might even get you to Mars within 30 to 40 days. That requires nuclear power, ion propulsion, and some kind of other technology that we're still kind of experimenting with. But there are ways of cutting down that transit time, and that means you're cutting down your radiation exposure.
Okay. Is that good for you, Dave? Or do you want to chime in a little bit more?
Yes, that was excellent. Thank you.
Okay, thanks. Okay, so now Adrian asks, let's see. Oh no, let's see. You were just saying that things were going well. Oh, Rowena asked if she thinks she's seen an image that suggests that some gamma rays are also emitted during solar particle events. Is that the case? Because we were talking about the difference between gamma rays and cosmic rays.
Right. the way that this tends to work is that when you have, for instance, the sun, when you have the sun launch what's called a coronal mass ejection, which is a huge cloud of plasma with a entrained magnetic field, that plasma travels very fast through the upper atmosphere of the sun, which you can think of as being almost pure hydrogen for the most part, which is protons. The thing is that that cloud gets compressed as it's traveling through this dense environment. That compression compresses the magnetic field, causes the particles to be accelerated to high energies. And so you wind up with what are called solar energetic particles. These are protons with energies of several million electron volts. And those are the energetic particles that travel to Earth within 20 minutes and can be a hazard for humans. Gamma rays are produced when these solar energetic particles, these protons, slam up against the nuclei of particles in your shielding or in your spacecraft bulkhead or even in your spacesuit. When those collisions happen, you get a gamma ray or two each time, and that contributes to your electromagnetic dosage. Radiation dosage for particles is one thing. Radiation dosage for electromagnetic radiation is a second factor. And both of those have to be taken and calculated separately to get your total radiation dose.
Interesting. So let's see if somebody else says something. Okay, fascinating. Okay, to check, in terms of balance, would the best time to go to Mars be one where a higher level of sunspots would be acceptable versus a lower level of cosmic rays due to fewer secondary particles and less exposure to dangerous cosmic rays that can damage DNA?
Yeah, very good question. As you've begun to understand, it's a balance between how much shielding you're willing to carry with you and how much radiation exposure you're likely to get over the duration of your trip. The worst situation is that if you planned at sunspot minimum when the cosmic rays are high, you would have to bring along a lot more radiation shielding, all right? Because there are going to be a lot more cosmic rays that you have to deal with. However, even during sunspot maximum, because the energy of the particles, the solar energetic protons, is 10 to 100 times lower than for cosmic ray particles, you don't need nearly as much shielding. So the bias tends to be that you really don't want there to be a lot of cosmic rays, and you're willing to put up with solar energetic particle storms that happen every few months. Because you're going to be using less shielding, it's going to be less costly, and you won't need as much thrust because you're carrying a lot less weight in shielding. So you know, there are trade-offs. In engineering, there are always trade-offs, and this is one, and it's all driven by these two cycles basically beating against each other and each producing a different radiation environment that you have to shield against. And shielding costs money, and it's weight, and weight is money in rocketry.
Okay, I think that's it for the ones in the chat. Hey, everybody, did I miss anything? Does anybody want to unmute and chime in?
Well, Adrienne, she asked the question, is there any research on the impact of solar cycles on species other than humans? Well, actually, there isn't really any impact that solar cycles have directly on humans either. I mean, you don't notice them. We're living down here at the bottom of a very thick atmosphere that shields us from, you know, the ebb and flow of the radiation in space. So, you know, we don't really notice it so much, except when we use a telescope and count sunspots, and that, or watch aurora. Now, aurora can produce human effects because over the course of time, they have had psychological impacts to humans. So that's one way that the solar cycle affects humans. But in terms of physical effects, no, they don't really produce any direct physical effects. And we don't we don't see any effects in humans or any other kind of biological life either.
All right. Anybody else want to chime in? Yeah, some new messages here. Electrical grid in 1989. Elaine, what are you talking about? Snowstorm hares, hares like rabbits. What is that?
I don't know.
Elaine, can you unmute and or write some more?
Now, I haven't mentioned anything about how the sunspot cycle affects Earth systems like satellites and the electric power grid. That is a whole subject in itself. So in that case, yeah, the solar cycle does affect humans in terms of the secondary changes they produce on the electric power grid and satellite communications and radio communications in the shortwave. But that's a technological impact, not a biological one.
Oh, and Rowena says, or Elaine says that the snowstorm hares was a autocorrect. That's too funny. All right, so there were, the 1989, Arwen was saying was electrical grid failure. I don't remember that one.
Yeah, that was March of '89. We had the Quebec blackout, and that was pretty spectacular. We've also had some near blackouts caused by space weather events like that. In Sweden and South Africa during 2003, the Halloween storm, we had power grid blackouts. But we've gotten better managing these things and predicting when they're going to happen. So I don't think we should see any more of those sorts of things happening. And also, our solar panels that we use in space are now of a different technology that's fairly immune to solar radiation exposure. So we no longer have the numbers of spacecraft outages and behaviors that we had during the late 1990s when we were using a different solar panel technology. So generally, our technology is moving in the direction of being more robust against solar storms. But we are still flesh and blood creatures that rely on shielding. So that really is the area that we're more closely studying these days, not so much technology mitigation.
Do you know of any sci-fi films or books or stories on solar cycles?
No.
I don't either. But that's a really fun question. I used to always use sci-fi short stories and films to get my students interested. So and we tend to have asteroids and, but solar storms would be a good one. Maybe we should propose it.
Yeah, maybe so. Yeah.
Okay. All right. So Kalish says Earth's magnetic field protects us from the cosmic rays and solar rays. Does keeping satellites near Earth protect the satellites from such blackouts?
Yes and no. The Earth's environment is a very messy environment. The most distant satellites are our communication and weather satellites, and those are out in geostationary orbit. And way out there, they have a lot of radiation exposure because they're in places where the Earth's magnetic field is the least stiff and provides the least protection. As we go inwards, we encounter what are called the Van Allen radiation belts, and those are really pretty grim. They produce their own radiation hazards to spacecraft that have really nothing to do with solar or cosmic radiation. They are their own system. And then finally, when you get into low Earth orbit, which is where the space station and other, communications satellites for the internet live, they are sort of in the upper reaches of the Earth's atmosphere and its exosphere. The exosphere provides drag against the satellites so that when you get below about 400 kilometers, the decay time for a satellite becomes, about 5 years or so. And at lower orbits, which are becoming more common, the decay time can be as short as a year or so. Now, when you have sunspot maximum, that means that the sun is producing a lot more X-rays from all this magnetic activity. Those X-rays reach the upper atmosphere of the Earth, heat it up, and cause it to expand out into higher orbits. So actually what happens during sunspot maximum is you have a lot of prospect for satellites to slowly lose orbit altitude and burn up in the atmosphere. Some satellites are specifically designed to end their lifetimes in that way, as a way of cleaning out low Earth orbits and getting rid of dead satellites. But others, that increase in the Earth's atmosphere resistance is not at all welcome. And so, satellite designers and these constellation designers have to be very aware of space weather effects and how those change during a sunspot cycle.
All right, well, I think that'll do it. So thank you very much. Several people say they can use this
Oh, good.
in their talks, and so that's great. That's what we're hoping for.
Mhm.
Remember that you can get the information, the slides and the recordings online, and
And
get
don't
the
forget to
article.
see the November issue of Astronomy Magazine, where I have an article about the discoveries of the sun in the last 10 years. So you can keep up with that.
All right. Thanks, everyone. See you next month.